So what I just showed you is the basic Lucas and Kanade method, kind of elegant. Basically, we've made a lot of assumptions, and these assumptions can give us errors. The biggest error we have, that is the assumption that we made that's in some sense the most wrong, is the idea that the motion is small, okay? Often, motion is large. And when motion is large, a couple of things are wrong with the Taylor expansion. One is, even if things are nice and smooth, they may not be linear. So we were doing a first-order Taylor expansion, not a second order, no second derivatives here. So that assumes that things are planar. Well, suppose things are curved a little bit. Well, we're going to handle that, in fact, we're going to talk about that in a minute, by doing something called iterative refinement, which is we're going to assume it's a plane, solve it, move the picture over a little bit, do it again, do it again, do it again, until we've converged finally to the right point. And it allows us to handle the non-planar component. But in some sense, even even worse than that is maybe I've got a nice bright pixel here, and then the bright pixel jumps over a bunch of dark pixels. So it's not even, and then there's some other, so it's not even local anymore. That is, I can't find where I went by just sort of following my derivatives. And the way we're going to handle that is with a course-defined method, which actually we're going to do next lesson. Today, this lesson, the only remainder thing we're going to talk about is this iterative refinement. So iterative refinement is designed to handle the fact that things are not exactly tangent. And so here's how it works. I'll write down the algorithm, and then it's a lot easier to see in a picture. All right? So the first thing is, the way you do it is, you say, OK, I'm going to pretend, I'm good at pretending, that it's just going to work. All right? So I solve for my velocities using the standard Lucas and Kanade. So I assume linear Taylor approximation. I solve for UV. Great. So now I've got a UV at every pixel. Now it says I'm going to warp IT to IT plus 1, okay? We talked about doing image warping when we were applying transformations. And those of you who are going to do the OMS problem set, you'll probably get to know and love how to do warping. But basically, the UV says how to move every pixel from one image to get to the next one. So you know what? I take this picture and I move all the pixels. And if you remember, we have to do this backward warp so we don't end up with holes. If you don't remember that, go back to the transformation lecture where we talked about warping. But the idea is that we essentially distort the T image to move to where I think all the pixels go. So it's almost the T plus 1 image. But it's not exactly the T plus 1 image, is it? It's close. So what do? I just do it again. I take the image that I created and I compare that to the real T plus 1 image, and I get a small amount of more motion. I could actually add that motion to the original motion. That's the new flow field. Well, I can take that one that I created, move it a little bit, and what do? Do it again until the pixels stop moving. And that will converge to a solution. So that's really easier seen here graphically.